Hi, welcome HL Physics Seminar students. This video is about Chapter 9.2, where we're going to look at single slit diffraction. And below, you can have a look at the learning objectives for 9.2. There really are not that many, and a lot of them are interconnected with each other. So our first learning objective is to sketch the diffraction pattern of a wave going through a single slit, and we'll have a look at that right away. So when we're sketching the diffraction patterns, these are the two most common ones that you may be asked to sketch. And one of the key things to really remember about A is that the middle one, I've actually got a sample down here, is the middle one is twice the size of the other ones. Okay, so these are 1 centimeter. The middle one has to be 2 centimeter. And this indicates the intensity of light. Likewise, over here, I actually have a better diagram for B below, so we'll have a look at that. We'll just go down and look at that right now. So in terms of B, it's essentially the same thing. So these two things, the other two nodes, the outer nodes and the central node is halved. So, the central node is double the other nodes. So 2B, whereas the other nodes are B. And so you might be asked to sketch a diagram, something similar to the waves that you see right here. Okay, the line in blue we'll talk about in just a moment. One of the things, though, that I want to note here is the intensity level is up to about 20 times larger than the first maxima from the central node. So if that's 20 times, this is only 1 times in terms of intensity. And you can kind of see how quickly that drops right here compared to the central. And each other one is a half-point reduction of the previous one. So there's a half-point reduction, which means this is going to be 0.5, and the one after that is going to be 0.25. The other thing that we're going to get into right now is the idea of measuring the intensity levels in terms of an angle. And this is a quick little radian warning. So we usually measure the stuff in radians. And so if we just have a quick look at this formula, we'll go into how this formula came about. So lambda is the wavelength of the light, and usually it is a monochromatic light. So monochromatic, mono meaning there is only one color, which means there's only one wavelength and one frequency for that light. The other thing is B is the width of the slit. So let's see if we can get a nice bright color here. So B, well, that's not showing up very well. B is this middle part right here, the width of that. And then theta, as we just mentioned, is the angle of separation. And this formula is usually better presented in this current format right here, where the wavelength and the angle increase and decrease proportionally to each other. And B, or the width of the slit, and the angle have an inverse relationship. So what that means is if we have a very small angle, we have a very large angle. So we have a very large angle here. And if we have a large slit, we have a smaller angle. Okay, now I'm gonna blow this piece up over here. And I'm just gonna redraw this right angle triangle. This is quite similar to the, what is it? It's quite similar to the down plane components or the inclined plane stuff that we looked at back with forces. So I'm going to label this in terms of the trigonometric information. So our angle is there, hypotenuse and opposite. The other thing to keep in mind is that these two angles here, so there is, if we had another line here and there was a right angle here, then this angle here would be the same as the one above. And so what we're really trying to do is we're trying to actually form a sine function here. And we're trying to say sine of angle theta is opposite over the hypotenuse. And we're going to bring that down here. We'll go a little bit further into that. The other thing to keep in mind, though, is that this diagram builds on Huygens principle. So remember Huygens principle, it goes on the idea that a point source, as it goes through a diffraction, so if we have a wave here, the idea here is that it's built up of multiple points, which also then create its own wavefront. Okay, and then so that kind of repeats on itself. That was Huygens principle. And so what this is really saying is that it's splitting the monochromatic light up into multiple pieces. And that's how we're getting that interference on this that we see and observe. So the next point is the diagram illustrates the deviation of lambda over b equals to theta. So it's just the derivation of the formula, and we'll get into that in just a moment. The other thing to also keep in mind is the path difference. X is leading to the first minima. So the first minima is where destructive interference happens. So it's where destructive interference happens. Destructive interference happens. And destructive interference always happens when the path difference is half a wavelength apart, or lambda over 2. So what we're going to do is we're going to make some substitutions. So I'm just going to redraw the triangle right here. Okay, so the hypotenuse is actually b over 2. The opposite side is our path difference. And because it's destructive interference, we're actually going to eventually replace that with lambda over 2. And then we have our angle theta. And so what we're really doing here now is we have sine theta. The opposite side is x. And we're going to replace that. I'm going to write that down as x first. That's the opposite. Now hypotenuse is b over 2. And we're actually going to replace x with lambda over 2. Lambda over 2. B over 2. And what that essentially does is that it allows us to cancel out the 2's. And again, they're always kind of cheating here. And what they're really saying is, hey, you know what? With sine of angle theta, let's just treat that as angle theta. And so if we clean this all up, we have, so we're cleaning all this up to be theta equals to lambda over b. And so that's sort of how this formula comes about, is through a series of trigonometry, building off of Huygens principle, and that this is leading to the first destructive interference. So that's what this diagram is representing, and that's how we built this very simple formula, which that really is mostly what you really need to know in terms of calculations. So below I've got 2 examples from Cognity, which we can go over, but first off I just want to quickly check back on our learning objectives. So sketching diffraction patterns, yep, we've done that. Okay, so that's something like that. Okay, or you might be asked to do the bigger ones, the rounded ones, right? Okay, so remember, if that's B, this is 2B. Okay, and likewise, if this is X, or sorry, I'm gonna do, just to keep this in line. If this is X, this here in the middle is 2X. So that's sketching interference patterns, or it could take on the form of we have a big central, then we have a middle, and it gets half the amount smaller. Okay, so as we mentioned, the middle part here is about 20 times larger. That would be 1 times, and each subsequent one would be half of that. Now you might be given something like, let's say you have half of this, you have the maxima, you might be given that, and it might tell you this is, it has a height of 5 centimeters, and it might ask you what the next one is, and again, that would be half of that, which is 2.5 centimeters. Okay? So that's the first learning objective. Second one, relate the shape of diffracted waves to the relative size of lambda and gap. So that was this part right here that we went through pretty fast. Okay, so how does the angle change? Okay, this little part right here. Okay, so as the wavelength increases, the angle also increases. So for example, so quick little test here, 700 nanometers is red light, and on the other end we have about 400, whoops, not 700, we have 400 nanometers, which is violet. Okay, so if we increase the wavelength, so if we're using red light instead of blue light, then we're going to have larger angle, which means if you use violet light, then we should have smaller angles. Okay, so it's understanding that difference as well as the gap size B, which we've already talked about right there. Okay, so those are the type of questions that you might get for the second learning objective. Describe the relative intensities of the central and the other maxima. We've just done that already. Okay, central maxima is always 20 times bigger for the central, and the other ones are half of the first, or of the next maxima before that. Okay, make calculations based on the formula. That's pretty simple. And comment on colors that will be seen if monochromatic light is not used. So I'll do this in a follow-up video. It's actually pretty straightforward. There's not a whole lot, but I'll cover that in a quick 1-minute video. Okay, examples 1 and 2. So example number 1 says coherent monochromatic light passes through a single slit. That is 0.5 millimeters. The central maxima on the diffraction pattern is observed to have width of 2.8 times 10 to the power of -3 radians. What is the wavelength of the light? Okay, so really we've got the width, that's B. We have an angle theta. What's the wavelength? Okay, so we apply our formula. I'm just going to do it right here. So our formula is theta, whoops, Okay, our formula here is theta, lambda over b. Make your substitutions. So it's going to be lambda times b, sorry, b times theta. And that's going to give us 0.5 millimeters. And we have 2.8, 10 to the negative 3. So don't forget that this is actually 10 to the negative 3 as well, meters. And we should have about 700 nanometers if you do that calculation, if you round that off. Okay, for example number 2, light of wavelength 200 nanometers. So we've got wavelength, lambda. So I like to make these little notes when I'm doing my questions. Through a slit of width b, so we're asked to find b. And it forms a diffraction pattern seen on the screen 3.5 meters away. Ooh, okay. This is actually looking like there's a little bit more information here maybe to throw us off a little bit. The distance between the straight through position on the third order minima is 0.14 centimeters away. Find the value of b. Okay, so we've got lambda. We don't have our angle, so we need to be able to find our angle first. And so it looks like we are probably going to have to do a tangent function. So quick little diagram here. Screen is 3.5 meters away, and this to the third order minima is 0.14 centimeters. So that is actually the angle. And so opposite over adjacent, so that's what we've got a tangent function that we need to do here. Okay, so if we punch that in, you should get an angle that is, sorry, I'll do the work in full here. So tan, angle theta, opposite, times 10 to the power negative 2, that's in meters now, 3.5. Okay, so if we compute that, we're going to get roughly 4 times 10 to the power of negative 4. Now keep in mind that was the third order minima. So what we actually need to do is, we're not quite there at the actual angle yet. This is 3 angles too big. So we need to actually divide this by 3, right? We have to kind of chop that up into 3 sections there. So we got to divide that by 3. So that is going to be 1.3 essentially, or 1.3 repeating. So the actual angle we want is this divided by 3, which is going to be 1.3 repeating, times 10 to the power of negative 4, that is, meters. Okay, so that is actually the angle that we've got. And we have our wavelength, which is 200 nanometers. Okay, now we do one last substitute. B is lambda over theta, wavelength 200 nanometers, or you can do 10 to the power of negative 9. So convert everything to meters first. 1.3 times 10 to the power of negative 4, and you'll get about 1.5 times 10 to the power of negative 3. I guess we can also write that as millimeters. Okay, so that is our solution. Okay guys, thanks for watching. Hope that was a good enough video for you. Please let me know if you have any questions about this particular chapter that has been quite short.